So, final part for this section is a BC-only topic called Euler's method. And this is a way where we can use tangent lines and a differential equation to estimate function values. So there are times in which we may have a slope field, we may have a differential equation, and we want to say, hey, from this, I know I can sketch an estimate of a particular solution, but I want to be able to use that sketch to calculate an estimate for a function. So we can use this when we don't need exact solutions. We can use this when we don't have time to find an exact solution. We can use this when, well, in the case of some differential equations, we can't solve them. It's actually impossible to separate them and find antiderivatives. That does happen. In which case, we want a method of reaching an estimate that is consistent no matter who's doing the estimating. So it's reproducible, much like a good science experiment where you want it to be reproducible results. We want a method for estimating that's reproducible no matter who does it. If you've seen the movie Hidden Figures, this is what they are doing in the movie to calculate the landing trajectory, is they're using tangent lines and a differential equation to estimate the different values needed. This is what's called an iterative method, meaning it is repetitive. We're going to follow the same steps over and over and over again until we reach where we're supposed to stop. For the AP exam, it's typically 2 repetitions, or what we call steps. So they may say something like, use Euler's method to estimate this using 2 steps. Occasionally, it's 3 steps. Technically, we've done it with 1 step when we did linearizations, but we just are going to take this further. So the general idea of this is, we're going to do this, use an example to kind of illustrate this. We're going to estimate f of 2.4 using Euler's method with 2 steps of increment 0.2. So this means we're going to repeat the steps twice. The increment of 0.2 is going to be how much x is changing by each time we go through the series of steps. So, and we're given a differential equation, dy dx equals x plus y, which is not easy to solve, and an initial point of 2, 0. So what it is we've been given a differential equation, we've been given a point that the particular solution has to go through, but we're not able to find the particular solution to calculate f of 2.4. So we're going to use tangent lines to estimate the f of 2.4. Now I could do this with 1 tangent line, but it's not going to give me a great estimate because I'm moving too far away from the point of tangency at 2, 0. So what we do is we're going to go part way and then change which tangent line we're using to be able to stay a little bit closer to the actual solution, even though we don't know the actual solution. So where we start is we write the equation of the tangent line at the point that we're given. So to write the equation of a tangent line, I need 2 things. I need a point, which they tell me is 2, 0, and I need the slope, which I have a differential equation, which tells me dy dx is x plus y. So with that point, it's going to be 2 plus 0, which is 2. So I have y minus 0 equals 2, parentheses, x minus 2. I do want to get y by itself for this. So y equals 2 times x minus 2 plus 0, which is just still, I don't need to write plus 0. And using this tangent line, I'm going to find a new point of tangency. And to do this, I need to know what a new x is. So my new x is going to be 2 plus my increment of 0.2. So my new x is 2.2. And I'm going to take this tangent line and see what's the y value when x is 2.2. Well, 2.2 minus 2 is 0.2 times 2 is 0.4. So my new point of tangency has the new x of 2.2, and by plugging that into my tangent line, I get a new y of 0.4, which I can see it's relatively close to the point I started at, but a little bit different. So now that's one step through this. I now need to take a second step, because they tell me to take 2 steps, and say, okay, let's repeat these steps. Using this point, let's go ahead and write the equation of a tangent line at 2.2.4. So my slope is, that tells me that dy dx is equal to x plus y. So my slope is 2.6. So I get y minus 0.4 equals 2.6 times x minus 2.2. I'm going to get y by itself just because of how I'm going to be using this. Oops. And then I'm going to use this. I have another new x. I'm going to take the old x of 2.2, add my increment. My new x is 2.4. I'm going to take that and this new tangent equation I have to find the y value. Whoops. Sorry about this. Y is equal to 2.6. 2.4 minus 2.2 is 0.2 plus the 0.4. 2.6 times 0.2 is 0.52 plus 0.4, which is 0.92. So my new point is at 2.4.92. Now I notice I've gone, that's my second step. That's how many steps they told me. And I noticed they wanted me to estimate f of 2.4. Well, I can see in my new point, the x is the 2.4 I'm supposed to use. So my f of 2.4 is about the y value in that point of 0.92. And I now have an estimate that everybody else who uses this method should also get when they follow these steps. It gives me a more accurate estimate than if I just used one tangent line, by breaking it up and saying, let's use one tangent line to get part way and a second, more accurate tangent line for the rest of the way.